previous module, we saw how we can reduce the project duration by incurring the least incremental cost of reducing the duration of activities on the critical paths. The method was cumbersome and is not appropriate for large networks. In this module, we first show how a linear programming approach can be used to calculate the earliest completion time of the project. This was calculated in an earlier module for the software project example using the forward pass through the network. Then, assuming a linear relationship between the duration of an activity and its direct cost, we extend the linear programming approach to find out the minimal incremental cost for each reduction in the project completion time from its normal completion time of 11 weeks. Then we show how the method can be adapted for finding out the project completion time that gives the maximum net return consisting of the bonus for completing the project early minus the incremental direct cost of reducing the activity duration. In case there is a reduction in indirect or overhead cost, which is often the case when the project is completed early, this reduction in indirect cost would be added to the bonus or revenue generated by completing the project early. Finally, we show how the same linear programming approach can be modified to handle a certain type of nonlinear relationship between the duration of an activity and its direct cost. To illustrate the use of linear programming approach to solve the problems mentioned above, we will use the same software project example that we considered for crashing in the previous module. Recall that the project has 8 activities with all the necessary data such as normal duration, normal cost, crash time, and crash cost are given in the table which is reproduced from the previous module. The precedence relationships are the same as in the previous module, which may also be inferred from the network diagram, which is also reproduced from the previous module. A linear program consists of a linear objective function to be optimized, that is maximized or minimized, subject to linear equality and or inequality constraints. A function f of n variables, say x1, x2 up to xn, is said to be linear if the function can be written as equal to a1 times x1 plus a2 times x2 and so on until we get to plus an times xn plus b, where a1, a2 up to an and b are specified constants. To understand the formulation, we need to first define variables whose values are to be determined so that the objective function is optimized, while at the same time satisfying all the constraints. The first problem we'll consider is the variable Si denote the start time of activity I. Then, for instance, Sa would denote the start time of activity A. Let T denote the completion time of the project. Now, to find the earliest completion time of the project, in this problem 1, the constraints and the objective function in the linear programming formulation as shown in the table. The objective function is minimize T. In this formulation, we have 2 sets of constraints, namely constraints on start times implied by the precedence relationships and non-negativity constraints. The constraint SB greater than or equal to SA plus 2 states that the start time of activity B should be greater than or equal to the completion time of activity A, which is given by the start time of activity A plus its duration of 2 units. Similarly, we have the constraints for the other activities. Note that the 2 constraints SC greater than or equal to SB plus 4 and SC greater than or equal to SC plus 3 together imply that SC is greater than or equal to the maximum of SB plus 4, SC plus 3, which in turn implies that the activity E can be started only after both activities B and C have been completed as required by the precedence relationships. The objective function is to minimize the completion time of the project denoted as T. There are 2 points worth noting. First, the equivalent constraints are shown on the right with all the variables on the left-hand side of the inequality or equality and the constant term on the right-hand side as required by many commercially available software. The second point is that all the variables are required to be non-negative. In general, a solution to linear programming may be such that some variables are fractional and not necessarily integer. Given that the duration of all activities are integers, we would want the start time of each activity and the project completion time to be integers. Fortunately, the structure of the constraints in the linear programming formulation above are such that an optimal solution will have integer values for all the variables. So we do not have to explicitly introduce constraints stating that the variables should be integers. Solving the above linear programming problem using the available software gives the project completion time t equal to 11 and the start time of each activities. The second problem we'll consider, we will modify the above formulation to find out the minimal incremental cost for each specified project completion time. In addition to the variables Si defined for each activity and variable t representing the project completion time, we define the following variables. Let Ri denote the reduction in the duration of activity from its normal duration. Then, for instance, Rb would denote the reduction in the duration of the activity B. Let alpha represent the reduction in the project completion time from its normal completion time of 11 weeks. The objective function is minimize 25 times Rb plus 25 times Rc plus 30 times Re. In this formulation, we have three sets of constraints, namely constraints implied by the precedence relationships, upper bound constraints on the reduction in activity durations, and non-negativity constraints. Several variables Ra, Rd, Rf, Rg, and Rh are set to 0 since no reduction is possible in the duration of the activities A, D, F, G, and H respectively. These variables can be omitted from the formulation, but we have retained them for illustration. The constraint Sb greater than or equal to Sa plus 2 minus Ra states that the start time of activity B should be greater than or equal to the completion time of activity A, which is given by the start time of activity A plus its duration of 2 minus Ra units of time, representing the duration of activity A after a reduction of Ra units of time. Similarly, we have the constraints for other activities. Given that the durations and the maximum reduction in the duration of the activities are integers, the structure of the constraints in this formulation also, as in the case of the previous problem 1, is such that solving the associated linear programming problem gives a solution in which all the variables are integers. So again, we do not have to explicitly introduce constraints stating that the variables must be integers. We solve the above linear programming problem for each specified value of alpha, starting from 1 and increasing it by 1 each time. Note that when alpha equal to 1, the project completion time t equals 10. The solution to the linear programming problem gives the minimum incremental direct cost for each specified reduction alpha in the value of the project completion time from its normal completion time of 11. The next problem, that is problem 3, we suppose the bonus for completing the project early is 50 per unit reduction in the project completion time from its normal completion time of 11 weeks. We want to maximize the net revenue, which is the bonus, including the reduction in overhead costs per unit reduction in the project completion time that is received, minus the incremental direct cost due to the reduction in the durations of some activities. Then the constraints remain the same as in problem 2, but the objective function is changed to maximize 50 times alpha minus 25 times Rb minus 25 times Rc minus 30 times Re. The objective function is to maximize the net revenue, which consists of the bonus of 50 for each unit reduction in the project completion time, minus the increase in direct cost due to reducing the duration of some activities. Solving this linear programming problem gives the optimal reduction in project completion time and the associated activity durations, all of them being integers, which in turn imply the associated increase in direct cost. The next problem, problem 4, is to address nonlinearity in increase in direct costs. The linear programming problem that we have formulated, that is problem 2, to find out the minimal incremental cost for each specified value of the project completion time, can be modified to handle a certain type of nonlinearity in the relationship between activity duration and its direct cost. We will illustrate this for the example we have been considering. Suppose now that the first unit of reduction of activity B costs 25, and the second unit of reduction of activity costs more than 25, say 30. Now, in the formulation of problem 2, we replace RB by RB1 plus RB2 in the constraints on start times implied by the precedence relationships. In the upper bound constraints, RB less than or equal to 2 is replaced by RB1 less than or equal to 1 and RB2 less than or equal to 1. In the non-negativity constraints, RB greater than or equal to 0 is replaced by RB1 greater than or equal to 0 and RB2 greater than or equal to 0. Finally, in the objective function, 25 times RB is replaced by 25 times RB1 plus 30 times RB2. Note that before the second reduction in the duration of activity B is taken, the first reduction in the duration of activity B should be been taken. In other words, RB2 equal to 1 should imply that RB1 equal to 1, or equivalently the constraint RB1 greater than or equal to RB2 should be satisfied. Note that the constraint RB1 greater than or equal to RB2, together with the restriction that the variables RB1 and RB2 must be integers 0 or 1, implies that whenever RB2 equals 1, we must have RB1 equal to 1. Fortunately, the objective coefficients of RB1 and RB2 are such that it is never optimal to have RB2 equal to 1 and RB1 equal to 0, because such a solution is dominated in terms of the objective function by the solution RB1 equal to 1 and RB2 equal to 0, with the values of the other variables remaining the same. Hence, for considerations of an optimal solution, we do not have to impose the restriction RB1 greater than or equal to RB2. With the above changes in the formulation of the problem, the structure of the constraints is such that an optimal solution will have an integer value for all the variables. So in this case also, we do not have to explicitly introduce constraints stating that the variables must be integers. It should be noted that for illustration, we have given the above 4 formulations for a small example. In practice, large linear programming problems can be solved routinely in a matter of few seconds or minutes, even if the problem is large-sized, say with several thousands of constraints and variables. Finally, in the unlikely case, suppose the second unit of reduction in the duration of activity B costs less than the first unit of reduction in the duration of the same activity. In this case, suppose the first unit of reduction costs 25 while the second unit reduction costs only 20. Now we must explicitly introduce the constraint RB1 greater than or equal to RB2, for otherwise may end up with a solution in which RB2 equals 1 and RB1 equal to 0, which is meaningless. Unfortunately, when the constraint RB1 greater than or equal to RB2 is explicitly introduced in the constraint set, the integrality property of an optimal solution may be lost. In other words, with RB1 greater than or equal to RB2 in the constraint set, a linear programming solution may have fractional values for some variables. We have to solve the problem as an integer programming problem, which differs from a linear programming problem in that some or all variables are restricted to be integers. Unfortunately, the time required to solve large-size integer programming problems is highly unpredictable, in that some problems are solved quickly while some others take a very long time, even with a fast, in terms of execution time, computer. This completes the module on using linear programming approach for reducing the project duration.